All right, folks, let's keep on keeping on. We're going to learn one more tactic and another form of proposition that we've actually already seen. You've actually already seen a bunch. So, the first form of proposition I want to show you is implies. So, we're going to use it to prove the following lemma, but I want to talk a little bit about this arrow first. So, it turns out this is the same arrow as in functions. We'll talk a little bit about that much later in the course. For now, it's just the same arrow. Uh, it defines implication. So we've already seen imp be as implication on booleans. Now this is implication on propositions. Okay, so the way a proof works with implies is you have to prove what's to the right of the arrow, but you assume what's to the left. So if what's on the left, called a premise, then you have to show what's on the right, a conclusion. So here's a lemma that uses implies. For all A that's a proposition, if A holds, then A holds. Oh, well, that seems straightforward enough. How does that work? Okay, let a proposition A be given such that A holds. So I've written intros with two things here to introduce both A and the hypothesis that A holds. Now I could have done this in two steps. I could have chosen a different name, right? You could call them whatever you want. My hypothesis that A holds. That's a little long. That's not how I would want to spend my time typing that. I tend to start my hypotheses with H, sometimes E, if it's an equality. Kind of depends. But H is a great one. We called it HA, so that's what the proof script says. So let a proposition A be given. This bit of the informal proof corresponds to the tactic intros A. Let it be given such that A holds. Call this hypothesis HA. That's this bit, this tactic. Okay, so now we have to prove that A holds. Well, we have two things in our context. A is a proposition, and HA is the assumption that A holds. So the thing to the right here says what you know. So here we know that A is a prop. Here we know that HA is a proof that A holds. So if we want to apply it, we would just say, well, I need to show that A holds. I know that A holds because of HA, so let's apply that knowledge. So you write apply, and your proof is complete. So we find A by HA. That's what apply means. So what does apply do? Apply takes something that's in your context and uses it directly. So you'll notice HA says that A holds, and we see it exactly. Okay, here's another example. This is a principle of logic called modus ponens. If P and Q, excuse me, if P implies Q, and you know P, then Q. Now, there's no and here, right? This is a little bit funny. This is a chain of arrows. So maybe a better way to say this, if P implies Q, then if P holds, then Q holds. And just like imp B, the else I'm not even going to write. Because if the premise of an implication, if the antecedent of an implication is false, it doesn't hold. Nothing doing, right? If pigs could fly, they wouldn't get so dirty in the mud. That's true, but it's a counterfactual. Pigs cannot fly. If frogs had wings, they wouldn't bump their ass when they hopped. True, maybe. I don't know whether or not frogs bump their butts when they hop. But in any case, frogs don't have wings. Same story here. Okay, how might this work? Well, for all propositions P and Q, here we've left off the type, but it's maybe clearer if I write it. For all propositions P and Q, if P implies Q, and if P, then Q. So just as a function that takes multiple arguments gets written with that curried type, we can kind of curry these implications, and it ends up having a meaning a lot like and, right? If you have this, then if you have this, then you have that. It's really the same as if you have these two things, then you have that. Let's see how the proof goes with tactics. Okay, let propositions P and Q be given. Okay, suppose that P implies Q, and further, suppose that P holds. Okay, let's look at our context again. What do we know? P and Q are propositions. We know, HPQ, that P implies Q, and we know that P. What we're going to perform now is backwards reasoning. So backwards reasoning says, well, look, I need to prove Q. I know that P implies Q. So P is sufficient to prove Q. Oh, wrong thing. Let me say it one more time. I want to prove Q. I know that P implies Q. So by HPQ, P is sufficient to prove Q. Okay. So what would we say in text? We would say something like, well, by HPQ, P is sufficient to show Q. Okay, cool. Well, now look at the state that we're in. We know P and we need to show P. Okay, great. This is just like above. Apply the appropriate hypothesis. Okay. So here's your first proof exercise. This is the first proof that you'll be doing in this course. It's like modus ponens, but we're going to sort of push it a little further. So for all propositions P, Q, and R, if P implies Q and Q implies R, and you know P, then you can show R. This approach will serve you well. This is what you'll be using so far. Okay, in the continuation, in the next few videos, I'll be talking about some other logical propositions and the way that we'll prove them. Any questions about this, feel free to ask on Zulip. I recognize this is a lot of symbolism and a lot of new stuff, so keep being patient with yourself. Talk to you soon.